conceptual. Uh, all important things are coming in today's class. Most important class actually, because these concepts will be used in all the further topics. So the topic is properties of center of mass. Properties of center of mass. Actually, the real topic starts from here only. This is the real topic. So let me update you on these properties. We defined center of mass. Center of mass is a location, a position. So we define the center of mass as follows. RCM is sigma MIRI by sigma MI. Or if I try to write in a more expanded form, M1R1 plus M2R2, so on, I can write MNRN by total mass, which is M. This is our fundamental definition of center of mass. And now what I will do is I'll just rearrange the terms. So this M, I'm going to take it to left hand side and write as M into RCM is M1R1 plus M2R2 plus so on MNRN. And I am going to call this equation as my first equation. This equation itself has got a deeper concept in it. Let me tell you what is the deeper concept. Suppose you stand on center of mass. You stand on center of mass. You didn't knew that you were standing on center of mass, but you stood there. You took your coordinate system in such a way that the origin is at center of mass. So without knowledge, you were standing at center of mass of these particles, and you took the origin there, and then you are like, okay, let me calculate the position of center of mass. So you stand on center of mass. Take the point where you are standing as origin. Take the point where you are standing as origin, and then try to find where is center of mass. Very interesting idea. So essentially, like in old age, sometimes we get forgetfulness. So some old people, suppose they want to put spectacles on their face and see, they forgot that the spectacles were in their pocket. Then they are searching the whole house. Where are the spectacles? Similarly, by mistake, we stood at center of mass. We stood at center of mass, and then we are taking that point as origin and then trying to find where the hell is center of mass. It is there only where you are standing. That means its position vector is 0. See, uh, if you are standing at some origin which is not center of mass, and if you find center of mass here, then this will be the position vector of center of mass. But suppose by chance you didn't know that you were standing at center of mass. Center of mass is here only, and you took that point only as origin, and then you are like, let me draw position vector to center of mass from origin. You are at origin and center of mass is at origin. Position vector will become 0. So we write this statement in this way, in a very strange way. The position of center of mass in center of mass frame. The position of center of mass. So I am trying to find the position of center of mass in center of mass frame. Look at this word. What does that mean? That means you are taking origin at center of mass. You didn't knew that, but you just casually took origin somewhere and it happened to be the center of mass. So position of mass in center of mass frame is always 0. This is the statement. So if you are standing at center of mass and trying to find the position of center of mass from your location, it will be 0. Okay, to give you an example, it looks like a very innocent statement, but We will use this statement in later chapters. When we go to rotation, in some proofs, we will use this statement. Suppose I have the following problem. Suppose there is a 2 kg particle and there is a 3 kg particle, and both are separated by 10 meters. And suppose I took my origin here. This is my y-axis. Let me try to draw properly. So this is my y-axis and this is my x-axis. And where did I take origin? Actually, I took it 6 meters from 2 kg and 4 meters from 3 kg. Just casually I took it there. I did not do any calculation or anything. I just said, okay, I'll take my origin here. And then now I am trying to find where is center of mass. Okay, the 3 kg coordinates are 4 comma 0. This is my y-axis and x-axis. So you see, on the x-axis you went by 4 meters and y-axis you did not go. Here is the 3 kg particle. So its coordinates are 4 comma 0 and 2 kg coordinates are minus 6 comma 0. So minus 6, let me write properly, minus 6 comma 0. And then I am trying to find where the hell is center of mass of these two particles. I am interested in the x coordinate only. Anyway, y coordinate is 0. So let's calculate. X coordinate of center of mass is m1 x1 plus m2 x2 by m1 plus m2, which is 3 into 4 mass into its x coordinate plus 2 into minus 6 by 3 plus 2, and it surprisingly becomes 0. That means center of mass is at origin only. So without knowing anything, I took origin somewhere and my center of mass happened to be there only. So I got 0. So position of center of mass in center of mass frame will be 0. When I say in center of mass frame, it means the origin is at center of mass. The coordinate system is at center of mass. That is the meaning. Okay, this is one thing which we will need in a later chapter. Now, let us do one thing. We will differentiate equation 1 with respect to time. Why the hell am I differentiating this? Because these particles could be moving. They are not in a fixed position, they are moving. And if that is the case, then the center of mass also could be moving. And I would like to find its velocity. So, the particles which you are considering, they could be moving, they need not be at rest. And as a reason, because they are moving, the center of mass could also move. So I am trying to find the velocity of center of mass. So let's differentiate equation 1 with respect to time. So what is the equation? M into RCM, I'm just once again writing it for clarity, is M1 R1 plus M2 R2 so on Mn Rn. So if I differentiate this with respect to time, note that masses are constants, they don't change. So when I am differentiating, I can keep mass aside. So m into drcm by dt, that is nothing but vcm. Rate of change of position of a particle gives velocity of the particle. So when I differentiate rcm, I get vcm. It is m1 v1 plus. Similarly here, m1 is a constant. When I differentiate r1, what is r1? Position of m1, and its rate of change gives velocity of m1 plus m2 v2 so on mn vn. This is what I got, and I am going to call this equation 2. Equation 2 tells us many things. Again, step by step, let us see what equation 2 tells us. First, using equation 2, I can calculate velocity of center of mass. Using equation 2, I can calculate velocity of center of mass if velocities of individual particles are known. If velocities of individual particles are known. So, if I know the velocity of first particle, that is v1, and if I know velocity of second particle v2 and so on, velocity of nth particle vn, if I know all of these, then using this equation I can even calculate velocity of center of mass. But this is not very important. It's okay, this is not bad, this is fine. There's something more about this equation, and that is the most important. You see, m1 v1, this term, mass into velocity, is called momentum. So this term m1 v1 is momentum of first particle. Momentum of first particle. Similarly, m2 v2 is momentum of second particle, and so on. And mn vn is momentum of nth particle. And then there is a plus symbol here, which means you are adding all these momenta. So ultimately, what you have here is momentum of the whole system. Momentum of the whole system. So this happens to be momentum of all particles. Momentum of all particles. That is how we have interpreted it. Now, what is on the left hand side? Total mass into velocity of center of mass. See what this statement is saying? If you want momentum of all particles, one way to calculate the momentum is go to first particle, ask that fellow, please give me your velocity, and multiply its mass and velocity. You got first particle momentum. Then go to second particle, ask that fellow, please give me your velocity, and you multiply the mass and velocity of second particle to get its momentum. And like this, you go to every particle, ask what is its velocity, find its momentum, and then add. But this is a very complex way to find momentum. The easier way would have been, don't go to any of these particles, just take the total mass, go to this fellow called center of mass, and ask what is his velocity. Okay, and then multiply both, and then you get the momentum in one shot. So see the beauty of this equation. If you have a group of particles and your intention is to find the momentum of the system, you need not go to individual particles. You can, nothing wrong, but that's a very complex way. Rather, you take the total mass and go to this fellow called center of mass, this point, and ask what is its velocity, and then multiply both. So the important thing is, momentum of system can also be calculated in a simpler way. Momentum of system can also be calculated in a simpler way as total mass into velocity of center of mass. This is the most easiest way to find momentum instead of going to individual particles. You know, for example, sometimes we will see later in other topics, there may be a ball, okay, and this ball is going forward and also rotating, and you want to find its momentum. I don't care about all the particles, just go to center of mass. This is center of mass if it's a uniform ball, and that fellow is moving with a velocity v, is always going in a straight line. After some time the ball may be here, but center of mass is always going in a straight line, right? So what is the momentum of this total mass of this ball into v? I don't care whether this particle is going like this particle is going like, because it's also rotating. All those individual particles, if you go and take their momenta and add and do all the calculation, ultimately the answer will be this only. See the beauty, how beautiful. If you have a big object, suppose you want to calculate my momentum, I am walking, you want to calculate my momentum, you come to my hand and say, hey hand, please tell me your velocity. Hey eye, please tell me your velocity. Hey mouth, please tell me your velocity. Hey ear, please tell me your velocity. And you're taking mass of hand into velocity of hand, mass of eye into velocity of eye, mass of ear into velocity of ear. This is very complex. Like this, if you go to every organ of the body and you are finding momentum and adding, too complex. Instead, my total mass, which is some 75 kg or whatever, into just one point somewhere in my chest, there will be center of mass. I will take that fellow's velocity and multiply both, and that is the momentum. Matter set. How beautiful it is. So powerful idea. So that's how you calculate the velocity of center of mass. You need not go to individual particles. Nothing wrong. You can go and do that way also. But this is much easier method. Okay. But the concept is not ending here. There is something more to this equation. More beautiful thing is there, which is the most useful concept. And that is this: momentum of the system, all the particles which you are taking in center of mass frame. You are now calculating the momentum of these particles in which frame? Not in ground frame. Previously, we were taking velocity of first particle in ground frame, velocity of second particle in ground frame, velocity of nth particle in ground frame, and then we found the momenta in ground frame. Right? But now what we are doing? We are doing it in center of mass. Momentum of system in center of mass frame will always be zero. How? Look, you are saying momentum of system by going to each particle. That's fine. But I do in a different way. I take total mass and take velocity of center of mass in ground frame and find momentum. But now I am in center of mass frame. If you center of mass frame means you are standing on center of mass and going along with it. If you stand on center of mass and go along with it, then velocity of center of mass in center of mass frame will be zero. You are going along with center of mass. So for you, center of mass is at rest. So in center of mass frame, velocity of center of mass is zero. I write like this: velocity of center of mass with respect to center of mass or in center of mass frame is zero. So momentum also will be zero. So if you are not convinced with this argument, let's do an example. Suppose I have a 2 kg particle going with 2 meters per second to the right. I have a 3 kg particle going with 4 meters per second to the right. Let's find the velocity of center of mass first. Velocity of center of mass is m1 v1, 2 into 2 to the right. Momentum is a vector, so you have to take direction into account. m1 v1 plus m2 v2, 3 into 4 to the right by m1 plus m2, which becomes 12 plus 4 by 5, which is 16 by 5 to the right. So center of mass of this system is moving with 16 by 5 to the right. Now what I got to do? I have to take a car and go with 16 by 5. Then I am in center of mass frame. I am going along with center of mass. So then what will happen in that frame? How to go to that frame? Add negative of your velocity to yourself and also to every object, right? That's how we go to a particular frame. If you want to go to some frame, you add negative of that velocity to that frame and all the objects in universe. So that frame comes to rest and you are looking all other objects in that frame. So you are in center of mass frame. The center of mass is at rest. Then what happens? The 2 kg now is having a velocity this way, right? 6 by 5 meters per second. And the 4 kg, not 4 kg, sorry, 3 kg is having a velocity 4 minus 16 by 5, 4 by 5, 4 minus 16 by 5 to the right. You see now what is the momentum for the 2 kg? Mass into velocity, 6 into 2 by 5, 12 by 5 to left, 12 by 5 to left. And what is momentum of this? 4 by 5 into 3, that is 12 by 5 to right. Momentum is a vector, so when you add this, you are getting 0. Why you are getting 0? Because you went into center of mass frame. In center of mass frame, momentum will always be 0. But the easiest way to understand that is, what is momentum? Mass into velocity of center of mass. But in center of mass frame, velocity of center of mass is 0. So momentum is 0. That's the easiest argument. Okay, that's the easiest argument. Okay, so most important statement is momentum of system in center of mass frame is always 0. Very important statement. Very important statement. Why is this important? Because later we will go into collisions and problems involving collisions, where sometimes you conserve momentum. Sometimes it depends on the conditions. You conserve momentum. But if you go to center of mass frame, anyway it is always 0. No need to conserve it. One equation will be less. It is always zero. In center of mass frame, momentum is always zero. So solving problems in center of mass frame will be very beautiful, easy. In ground frame, if to solve the problem, you have to conserve momentum and let's say energy. In center of mass frame, anyway, momentum is always zero, so you need not bother about it. Just conserve energy and you'll get the answer. Beauty. So it will simplify our, you know, discussion to a great level at a later stage. So very important idea. So two things. If you see the beginning, I told you position of center of mass in center of mass frame is always zero. Beautiful concept. Now I am coming to the next concept. Momentum of system in center of mass frame is always zero. That's why center of mass frame is also called zero momentum frame. Zero momentum frame. In that frame, momentum is always zero and you need not worry about it. It is always zero. Center of mass frame is called zero momentum frame. Okay. Ground frame is called a laboratory frame. All our laboratories are located on the ground only. No? So ground frame sometimes is called laboratory frame, and center of mass frame is a different frame. It's called zero momentum frame. Okay. So these are the most important properties. So position of center of mass in center of mass frame is zero. Then momentum of system in ground frame is total mass into velocity of center of mass. Let me write that also. Momentum of system in ground frame is total mass into velocity of center of mass in ground frame. You can even generalize this. Momentum of system in car frame is total mass into velocity of center of mass in car frame. Momentum of system in rocket frame is total mass into velocity of center of mass in rocket frame. Now, momentum of system in center of mass frame is total mass into velocity of center of mass in center of mass frame, which is zero. That's why momentum of system in center of mass frame will be zero. Very important and powerful idea. Okay. So what are all the things we got using equation 2? One, we can calculate velocity of center of mass. That is one thing. And it is also telling that total momentum, if you want to find, no need to go to each particle. Take total mass and just multiply with velocity of center of mass. And third is momentum of system in center of mass frame is always zero. These are the three important things. It is not over. Now what we will do, we will differentiate equation 2 also. Why the hell are you differentiating it now? Because the particles could be accelerating. Previously we differentiated saying that the particles could be moving. They could have velocity. Now I am saying particles could accelerate. Next step. So we'll once again differentiate equation 2. It will give us even more deeper ideas. And that's the final. We don't differentiate any further. Because even in kinematics also, we differentiated position to get velocity. We differentiated velocity to get acceleration. And that's enough to solve all kinematics. If you know up to acceleration, we can solve any kinematics. No need to go to rate of change of acceleration again. Not needed. It is called jerk, by the way. But it's not needed. Similarly here, I got the position of center of mass. That is equation 1. I got the velocity of center of mass, that is equation 2. I go just one more step ahead and find acceleration of center of mass. So differentiating equation 2, we get total mass into dVcm by dt. I let it as ACM, acceleration of center of mass, is m1a1, okay, plus m2a2 plus so on mnan. I call this equation 3. Again, very important, and again it has very deep concepts embedded inside it. Let us look at it step by step. First point, okay, point number 1. I can use equation 3 to find acceleration of center of mass if I know acceleration of all the particles. That is very obvious. If you know acceleration of first particle, second particle, and nth particle, I can use this equation to find acceleration of center of mass. So that's very obvious. I'm writing it. If you knew the acceleration of each particle, I could, with the help of equation 3, I could, with the help of equation 3, find acceleration of center of mass. That's very obvious statement. There is nothing special about that. But let's have a deeper look. What is M1A1? If you look at it from Newton's second law perspective, this should be equal to the net force acting on M1. So I can any day replace M1A1 with the net force acting on M1, because Newton's second law says net force on a particle is mass of the particle into acceleration of the particle in certain inertial frame. Okay, we are right now in ground frame, which for all experiments on the earth is inertial. If you want to do some experiment on celestial bodies, earth is not inertial. You must choose some other good inertial frame. But for the phenomena on earth, okay, like you are observing a car moving on the road and so on, we neglect the acceleration of earth. It's very small, so we treat earth as inertial frame. So this first term M1A1, so I'm going to write equation 3 again here on the next page. So let me write it once again. M into ACM is M1A1 plus M2A2 and so on, Mnan. So this term, by Newton's second law, it gives total force acting on M1. Similarly, this gives total force acting on M2 and so on. And this gives total force acting on Mn. So if you add all this whole thing is giving total force on all these particles. Total force on all these particles. So this is giving total force on system. I am considering all particles as one system, so it gives total force on the system. Now, of course, I can say total force on the system is mass into acceleration of center of mass, but let me go much more deeper here. In this total force on the system, that is total force on M1 plus total force on M2 plus so on total force on Mn. In these, there are also forces which are internal. What is meant by internal? M1 may exert a force on M2 and M2 will exert a force on M1, like action reaction pair. What are these forces? They can be gravitational force between M1 and M2, or if M1 and M2 are some kind of charges, they have some charge on them, it can be some electrostatic repulsion and so on. So let me show some figure here. Suppose this is M1, this is M2, this is M3. Let's consider three particles. Okay, now some fellow came and applied a force on M1, that's an external force, and some fellow came and applied a force on M2, that is also an external force, and some fellow came and applied a force on M3, that is also external force. These are all external. Some external fellow came and is pulling these particles. But not just that, M1 could exert a force on M2. Why? That may be gravitational, because any two particles having mass will attract each other, or it could be electrostatic or whatever. This is force on 2 due to 1, force on M2 due to 1. And if M1 exerts force on M2, by Newton's third law, M2 will also exert force on M1, that is force on 1 due to 2. These two are internal forces, right? What M1 exerts on M2 and what M2 exerts on M1. Okay, and in mechanics, these internal forces always come in action reaction pair, where they have same magnitude and opposite direction and even same line of action. They are acting along the same line. Okay, so internal forces come as action reaction pair. So whatever force M1 exerts on M2, M2 exerts a force of same magnitude on M1. These forces will have opposite direction. These forces will have opposite direction. They are equal and they have same line of action. That is a very important idea in mechanics. It is called Newton's third law in strong form. Sometimes, it so happens that The forces, if you go to electromagnetism and other chapters, not mechanics, there the forces may have same magnitude, but sometimes may not have opposite direction. Or even if they have opposite direction, their lines of action may not coincide. One force will be like this, other will be like this. That might create a torque also. So we say when forces are equal in magnitude, opposite in direction, and along the same line, then we say Newton's third law is obeyed in a strict form, strong form, strong form. We say strong form of Newton's third law. In mechanics, it will always be obeyed in the strong form. Okay, Newton's third law. When we go to electromagnetism, we have problem with Newton's laws. They may not be obeyed. Okay, when you go to speeds very close to speed of light, Newton's laws will fail. You have to take up relativity. Or when you go to the subatomic world where size is extremely small, Newton's law will fail. We have to go into quantum mechanics. Newtonian mechanics will not work. All these are limitations are there for Newton's laws. But for our discussion right now, no limitation. Newton's law is the God. So these internal forces will cancel. Why? Both have same magnitude and opposite direction. Similarly, M3 may attract M2 with a force which I call as force on 2 due to 3, and M2 will attract M3 with a force which I call as force on 3 due to 2, and again these two will form action reaction pair, right? They have same magnitude and opposite direction, they cancel. So what I am trying to say, when you write total force on M1, it also includes force on M1 due to M2, M3, M4, so on. Similarly, when I write total force on M2, it also includes force on M2 due to M1, M3, M4, M5, and so on. Similarly, when I write total force on Mn, it also includes force on Mn due to M1, M2, M3, M4 up to M minus 1, Mn minus 1. All these internal forces will cancel. Can you see that? They come as action reaction pair now. F12, F21 cancel. F23, F32 cancel. F13, F31 cancel. If there is another particle, F14 and F41 will cancel. F24 and F42 will cancel. So all internal forces will cancel. Which means I can write this, instead of writing total force on system, I can write this as total external force on the system. Internals have cancelled. Total external force on the system. Internal forces among the particles came as action reaction pair and they got cancelled. Because in mechanics, Newton's third law is obeyed. It's the strongest form. No problem. This is what we are getting. So what the hell am I getting? Total external force on the system. That is what I'm getting on the RHS. And on the LHS, what I have? Total mass into acceleration of center of mass. Let's write it. F total external, internals cancelled, on the system. System means group of particles. Total external force on all the particles is total mass into acceleration of center of mass. You see, this is exactly Newton's second law again. But you are now not applying to just one particle. You are applying Newton's second law to a group of particles. And now the concept is this: when you apply Newton's second law for group of particles, for 2 particles, 3 particles, or 100 particles, and when you write F equal to ma, F is the total external force on the system, m is the total mass. The question is which a? If there are suppose 3 particles, whose a are you taking? Are you taking a of this or a of this or a of this? No, it's not a of first particle or a of acceleration of second particle. We are taking acceleration of center of mass of all these particles. That is what you have here. So when you apply F equal to ma to single particle, then F is total force on that particle, m is mass of that particle, a is acceleration of that particle. But if you apply F equal to ma for a group of particles, then F is total external force on that group, internals cancelled. M is the total mass of that group. What is A? It is not acceleration of any one of these particles. It is acceleration of center of mass of the group. That means F equal to ma, if you apply to single particle, you get that particle's acceleration. But F equal to ma, if you apply for group of particles, you get acceleration of center of mass. So Newton's second law, when applied to group of particles, gives acceleration of center of mass of the group. Let me help you understand this. Suppose you look at this beautiful example. Suppose I have a ball. Okay, I have a ball and it's lying on, let's say, is frictionless surface. That is a frictionless surface. This ball has mass m. Suppose I am applying a force F here. Ball contains so many particles. This ball is made up of zillions of particles. There is no other horizontal force. Vertically there is mg and n, they cancel it. Let us say there is no other horizontal force. Suppose I apply F equal to ma horizontally. F is the horizontal force, m into a. This a is for which fellow? Not any one of these particles, but acceleration of center of mass. This point which is there on the body here. It's a symmetric object, right? So center of mass will be there. So you are getting acceleration of this fellow, the acceleration of center of mass. I'll tell you when something very surprising also. You may apply this force here, or you may apply this force instead of there. No, instead of there, you apply this force here. No problem. Still you get same acceleration for center of mass. Or you apply that force at the topmost point. I don't care where you apply, as long as it is on the body in the same direction. Wherever you apply, you get acceleration of center of mass only. This is a beauty. So F equal to ma, when you are applying for a group of particles, the a there will be acceleration of center of mass of the group. So Newton's second law, when you apply to group of particles, gives acceleration of center of mass of the group. This is the concept. Now it's not yet over. Not yet over. So the next part is more interesting. Suppose if this total external force on system was zero, internal forces anyway came as action reaction pair and they added to zero. But now I am putting a condition that even external force on the system, on the group of particles, is zero. Then acceleration of center of mass will be zero, or velocity of center of mass is constant, or total mass into velocity of center of mass is constant. Means momentum of the system is constant. That is law of conservation of momentum in its exact form. See the beauty? If external force on group of particles is zero, momentum of those particles will be conserved. One particle's momentum may increase, other may decrease, but total momentum will remain same. This is an important concept. Not only that, if external force on system is zero, velocity of center of mass is constant, means center of mass will do whatever it is doing. If it was at rest, it remains at rest. If it was moving in some direction with some speed, it continues in same direction with same speed. If external force on system is zero, center of mass will not accelerate. Other particles may accelerate, but center of mass will be there also. This is a very beautiful example on this, which is what I want to discuss. But before that, I just want to revise once again from the beginning. Whatever I am telling you today is the crux of this chapter. The calculation of center of mass, integration, blah blah blah, all that. Anyway we have done it. Everybody will do. That is not very important. Most important is this only. Most important. So first, position of center of mass in center of mass frame is always zero. Very important. Next, momentum of system in center of mass frame is always zero. That's why center of mass frame is also called zero momentum frame. Then total force acting on the system will result in acceleration of center of mass. Total force acting on the system is total mass into acceleration of center of mass. If total external force on system is zero, then acceleration of center of mass is zero. Velocity of center of mass is constant. It will not act. It will, if it is at rest, it remains at rest. If it was going in some direction with some speed, it continues to go in same direction with some same speed. Also, momentum is constant. Law of conservation of momentum comes from here also. There is another way to look at momentum. I'll talk about that later. But you can argue from here also. So all these concepts are there. Now, particularly this idea that if Total external force on system is zero, velocity of center of mass is constant. I'll tell you in a very interesting example. Suppose there is a bus. Okay, there is a bus, and let's say you are inside the bus, you are trapped inside the bus, and I cannot open any window. All windows are closed, they are sealed. All windows are sealed, all doors are sealed. You cannot open any window, there is no hole, nothing. Bus is sealed. You are trapped inside the bus, let us say. You are trapped. Now, this is a very smooth road, let us say, no friction, very hypothetical case. And your mom is here. She is waiting that you will come home. She is waiting. Nobody is there to help you. Okay? There is no hole in the bus through which you can throw something or whatever. You cannot open any windows. Everything is sealed. Now I'll tell you something very interesting. If you see the total external force on you plus bus, this system is zero. External force is not there. Nobody is coming and pushing you, the bus. So no external force. So acceleration of center of mass of this system, u plus bus, is zero. So velocity of center of mass of this system, u and the bus, is constant. But right now u and bus both are at rest. So center of mass is also at rest, so it is zero. So the center of mass of bus plus u is zero. Center of mass of bus plus u is zero. It is there only, it is not moving. Who can accelerate center of mass? Only external forces. We saw that only external force can accelerate center of mass. Internal forces cannot accelerate, they all cancel anyway. But there is no external force. So center of mass cannot accelerate, it is at rest. Now you want to reach your mom. So what you do a stunt. Like the film hero, you jump in the bus and with your legs, means like this. Let me show you. You jump in the bus and with your legs, you kick the bus like that. So your idea is, I will keep kicking the bus like this and bus keeps going forward and one day I will reach my mom, and then from the window which you cannot open, your mom will see you at least, and then she'll bring a hammer and break the window and rescue you, suppose. But your idea is flawed. You are thinking I'll jump like this and hit the bus and the bus will go some distance forward and again I'll jump and hit like that. But it is impossible. Why? I'll tell you. When you hit the bus starts. These are internal forces. There is no external force on the system. So center of mass is there only. It is at rest. It cannot move. Wherever is the center of mass of your system. Now when you hit the bus goes forward. You come back. Center of mass is there only. It is not moving an inch. Then suppose the bus came forward. You ultimately came back here. Okay. The bus cannot keep going because at some point you will hit the bus backside also. And as a result, you stopped, bus also stopped. But center of mass is there only. Then you walk forward, but bus will come back now again. Because how do you walk? You push the bus back to go forward. So you go forward, bus comes back. Again, you are at the same starting point only, here only. Then again, you jump and hit the bus. Bus goes forward, you come back. Then your head will hit back of bus. As a result, bus will retard and stop, you also stop. Again, you walk on the bus in the forward, bus will come back. Whatever you do, you cannot reach your mom. Center of mass of the system never moved also. If I come and push the bus, then center of mass of bus and you will move and you will reach your mom. That is okay. But in this case, you try whatever. There is no window openable also. If window was openable, then from the window you will throw bag that side, bus will come this side and bag will be going left, bus will be coming to right. Center of mass is there only, but at least you and bus will reach your mom then, because bag is gone. But no window was openable. No window was openable. Everything is sealed. So how you will reach your mom? You cannot reach. This is what physics says, and that is the correct concept. You are thinking I will perform a stunt like the hero or heroine, and kick the bus, continuously kick the bus, and it will reach your mom. No, it will not reach. You kick bus forward, you go back. Then your head will back of bus, and you stop, bus stops. Then you walk forward, bus goes backward. You walk back, bus goes forward. Center of mass is there only all this. It will not move an inch. Why? No external force. And center of mass was at rest, so it will not accelerate. You may accelerate, but bus will accelerate in reverse direction. Center of mass is there only. You may stop, bus will stop, but center of mass is there only. You run, bus will run, but center of mass is there only. You cannot reach your mom. If you have any counter argument for this, you present that argument to me and I'll prove that it is wrong. Because people argued with me in different ways. Sir, I have magnet with me inside the bus. Then I'll put one magnet here and I'll hold another magnet here. And this magnet will attract this and bus will come towards me. You also go towards bus, obviously. So you might meet here. Then when you want to separate and come back, again bus will go back. So you are ultimately there only. Whatever you do, internal forces cannot accelerate center of mass. Beauty. The beauty of physics. I hope this argument is clear. So this is the idea that I am trying to tell you related to this equation. Okay. So these are the concepts which we will use in our problems, in our calculations. Let me take one example. Let me take one example. Suppose I have it's a very beautiful example. These kind of problems we keep doing. Suppose I have a plank like this. Plank, and it is kept on a frictionless surface. Plank has mass m and plank has length L. So there is no friction between plank and ground, but there is friction between the person and plank so that he can walk on the plank. Person's mass is m. The question is, what is the distance moved by the plank by the time person reaches this end? That is the question. What is distance moved by plank by the time person reaches right end of plank? We can do it in a very systematic way by taking proper coordinate systems, which we will do initially. There is also a shortcut to do this kind of questions. We'll do that also. Now, first thing, let us understand the physics behind the problem. Why should the plank move? Look, the person is going this side. How he is going? In order to go to the right, there must be a force on his leg to the right, and that force is frictional force. So how do you walk? One leg is on the ground and the other leg and the body are trying to go forward. How they are trying to go forward? With the leg on the ground, you are pushing the ground back. Suppose if I show one leg with a shoe like this, I am drawing a very bad diagram obviously. So with this foot, you are pushing the ground back, and the ground will in turn push you forward, and this friction will be static because the shoe is not moving with respect to ground. This shoe which is on the ground is, if it moves, we will slip and fall down. It will break our bones. So the foot which is on the ground is not moving. Remaining part of the body is moving forward by taking the support. That's okay. So there is a static friction on the foot in the forward direction. Okay. So this person who is walking on the plank, on him there is a static friction on the foot in forward direction, and hence he is walking forward. Simple. If you want to go forward, there must be a force on you in the forward direction if you are starting from rest. The reaction of this acts on the plank. Now, the plank is on a smooth surface, so this force on the plank will take it back, obviously. So the plank will go back, you go forward. So by the time you reach here, the plank would have gone back. So how would this situation look like? Let me show it on the next page. So you started from here, okay? Sorry, just 1 minute. Started from here, and I'm just drawing it below. By the time you come to the right end, let me call the right end as B, the plank moved a bit. So the final scenario looks like this. You reached the right end, but plank in the time moved to left, and so ultimately, the situation is like this. This is exactly again the similar example to that bus. Suppose your mom is waiting here. You want to reach with the plank to your mom. Okay, you can't reach. Suppose even otherwise also I'll tell you. Suppose you say, okay, help with the plank. I'll jump from the plank and reach my mom. You can't because this is smooth floor. Then you can't walk. You'll just move your legs. So either way, now also we are in trouble. We can't reach. So anyway, you go forward. There is another way. There is another way. You can do a jump from the plank by pushing the plank back, and you continue to go forward and reach your mom. That is there. But anyway, let's come to the problem. So when you walk to the right, the plank moved to the left, and he's asking by how much distance the plank moved. What is the idea here? External force on this system in horizontal direction is zero. Okay, vertical also it is zero, but I'm just saying horizontal is much better. Vertical, there may be other problems. The center of mass of the person goes up and down when he's walking and all that. So let's not talk about vertical. Horizontal direction, external force on system is zero. If external force on system is zero, center of mass will not accelerate horizontally. Initially, center of mass was at rest. So center of mass will always remain at rest. So if you walk forward, plank comes back, but center of mass is there only. Then again, if you walk back, plank goes forward, center of mass is there only. It is not moving. Okay, that is our idea. So using this idea that center of mass doesn't move, we can find how much the plank moved. Okay, if you moved forward, you moved a length L na forward, but plank took you back. So ultimately, let's do it properly with a coordinate system. First, let's do it with a coordinate system. Then we will do it in an easier shortcut way. I am fixing my coordinate system to the ground. Coordinate systems are fixed to the ground. They don't move. You might move, plank might move, but coordinate system is not moving. So coordinate system fixed to ground. Okay. Now my mass is M, plank mass is capital M, and plank center of mass is here. My center of mass is somewhere here. Okay. Where is the net center of mass of the system in the x direction? So I'll calculate M into L by 2, because Planck's center of mass is at L by 2, plus M into 0. Person is right now at origin, so his center of mass is 0, by M plus M. This is the x coordinate of center of mass of the system. This will remain the same. It will not change. Why? Because external force on system is 0. If external force on system is 0, acceleration of center of mass is 0. If acceleration of center of mass is 0, velocity of center of mass is constant. But initially center of mass was at rest because both person and Planck were at rest. So center of mass is not moving. It is wherever it is. It will never move. So this is where center of mass is. Now after some time, what happened? After some time, I am redrawing this figure. Okay, coordinate system is fixed to the ground. Let me draw with blue color only. I'm just redrawing the figure down. Coordinate system is fixed to the ground. It did not move an inch. But Planck came back like this. Person went forward. When person went forward, Planck came back. Coordinate system is there. Let us say Planck came back by a distance x. Okay. Then how much actually the person got displaced? He went L on the Planck, but Planck brought him back also by x. So effectively he is at a position L minus x, right? See, he walked on the Planck, but Planck was moving back now. So he came back along with the Planck, right? So ultimately when he reached to the right end, he traveled L forward and x backward. So effectively he traveled only L minus x forward. Okay. Now Where is the net center of mass now? So m into person's mass into his center of mass is, let me just put it here only, L minus x. Coordinate system did not move, only the person and the Planck moved, plus capital M into, where is this center of mass? If you say this is L by 2, it is L by 2 minus x, its coordinate. L by 2 minus x by m plus m. This is the coordinate of center of mass now. This is the coordinate of center of mass previously. But center of mass coordinate never changed. It was there only. It never moved. Person moved, Planck moved. Center of mass did not move. So we can equate both of these. And from there we can calculate x, how much Planck moved, right? So m into L by 2 by m plus m is equal to, what is this, ml minus mx plus ml by 2 minus mx by m plus m. You can cancel this, and after that you get ml by 2 is ml minus mx plus ml by 2 minus mx. This also cancels. So from here x will be ml by m plus m. What is x? The distance by which Planck moved. So Planck moved so much. So when you walked forward, Planck went back by this amount. Center of mass of you and the Planck is there only. It did not move an inch. This is what happened. How to calculate this in an easier way? Let's see. See, originally center of mass was here. So when you moved some distance, you are changing center of mass by m, your mass into whatever you moved in the ground frame. Similarly, Planck moved this side. So m into whatever Planck moved, both these should be equal to keep center of mass there only. So your mass into your effective displacement to the right should be equal to Planck's mass into Planck's effective displacement to the left. This is shortcut, I'm telling you. This is shortcut. Actually, how do you get this shortcut? If you take coordinate system by mistake at center of mass itself, origin, okay, then person moved some distance, Planck moved, center of mass moved some distance, his mass into whatever he moved and its mass into whatever it moved, both should match to keep center of mass here only. Like for example, m1x1 plus m2x2 by m1 plus m2 is original center of mass. Suppose he moved by distance a, m1 into x1 minus a, then m2 into x2 plus b. These terms should cancel now to keep center of mass there only. So mass into whatever he moved in one direction is this mass into whatever it moved in the opposite direction. Then only center of mass will remain there. That's our idea. That is a faster way to do it. So let me do with that method and tell you how to get the answer. This is a much faster method. Let me delete this. You see here, suppose when the person moved to the right, the person was originally like this. When the person moved to the right by L, Planck moved to the left by x. So effectively how much person moved? L minus x to the right. And how much Planck moved? X to the left. Mass of the person into effective displacement to the right is mass of Planck into effective displacement to left. If I equate this, then what do I get? X as ml by m plus m. One step you got it. Whatever you got with all this calculation, ml by m plus m, you got it one step. So what I am saying, suppose there are two objects, center of mass is here, okay, and external force on the system is 0. So these objects are moving due to internal force. This object is attracting this and that object is attracting this. So after some time, suppose this object came here and this object came here, center of mass will remain there only. So what is the relationship? Whatever is mass of this object into whatever it moved to the right will be equal to whatever is mass of this object into whatever it moved to the left to keep center of mass there only. This is the logic which we are using. Very important idea. So I'll stop here. We will continue this with many more examples and many more ideas. And ultimately, after that, we will go into collisions. That's the continuation of this chapter. We'll go into collision theory. Two bodies come and collide. What will be velocity after collision? Will they stick after collision or will they move separate? And all those ideas we will check. We will do that. So, any doubts still here? So, you go through this.
No, sir.
Go through this once again. This is a very important lecture. This is the crux of this chapter, actually. Whatever I told you today, this is the crux of center of mass. Okay, I'll send you these files.